Hopefully it starts to look better than that. Let's try it again. Wow, that sucks. Oh, all right. All right. So last day we were talking about being able to use some of the debug. Now there is the whole Cortex family of CPUs has a whole piece of silicone dedicated to being able to send debug information out, and we're going to look at some of the different options for doing that. One of the things that we can do is we can just go to debug, and it'll by default stop at the first line of code, and then you can single step through your code. And you can step over a line of code, which means run this and then come back to me. So however many assembly language instructions that takes, I don't care, go do it, and then come back to the next line. You can step into uh, uh, functions or lines of code if it's calling other things by just going step into, and it will go to that function, and then you can step over the individual lines. And there's also a step return where you can then say, I've had enough, get me back to the main bit of code. And every time you step through one line of code, you can then go and hover over the different variables, and it will tell you what they are if they're in scope. And so if I'm in a function and I have a count and I hover over count, and then I have a count plus plus, and then I hover over the count, it'll show me it incremented one line. So you can do that kind of thing. It also quite frequently in the debug window over on the right hand side will show you the different variables that are currently in scope, and it will show you what they are. If you want to have a look at this stuff when it's running, as it's running, then we would use the back channel, the SWV back channel, to be able to look at our data trace. And data trace will allow you to put 4 variables, and it says either give me the address of the variable if you happen to know it, or what is the name of the variable. So as long as it doesn't go in and out of scope, like I say, so you put them up global, let's say we have count or position or A to D value or what have you, then putting something in that debug window, you'll be able to see the data. So let me just see if I can go here and go debug. Now, in order to make that back channel work, you have to, in debugging, initialize the serial wire viewer part of it. And so here I have the data trace window open, and the data trace window I got from window, show view, the serial wire viewer, and the serial wire viewer. I have different graph things available, but data trace is what I was looking at. The one, again, there's a graph, and data console is if I redirect printf. So I've got those both open here. Both of them go to the same configuration. You open up the little tool window, and then it'll say, okay, I've got a different comparator. So it's comparing values. So when it sees the variable or address count, then it will match up and give you that data. Now it does it in the back end at various times. Okay, so it's going, and some of you in lab have seen where it says, oh, it's overflowed, something like that, because you can push data out far faster than it's able to display it. So oftentimes what you want to do is in your while one loop, put like a delay of 200, 250 milliseconds so it doesn't update it as frequently and it's able to keep up, okay? And so we can put 4 different variables. And then the nice thing about it is you don't really have to do anything. It'll just start showing up here as long as I've enabled that debug in the debug window. And so the other part of it is if I redirect printf. And again, that's in the week 2. It says setting up clocks and debug. And so for doing the console, there's what's known as stimulus ports, and the Cortex system gives you the ability of setting up 32 channels, so I can redirect information all over the place. By default, they have port 0 enabled for you. You have to do a little bit ITM send character, which is what we're going to redirect printf to do. Will go out port 0. If you want to go out other ports, you have to roll up your sleeves and go a little deeper. The ITM send character just by itself will go out port 0. So in order to do that, I need to check it off and say, hey, I want to go out port 0. So if you've done all of that, then hopefully when I do a printf, you're going to see it in this data console. Okay, so this is data trace. That's what you're going to see. That's where you'll see these. And if you have this checked off, that's the data console is where you're going to see the redirected printf. Now, if I look at, let me just, so you see I'm at the very first step and we said, okay, the step over. So if I step over, it runs hell and it goes to the next line. System clock config. I want it to do that whole function and go to the next line, so I can just do that. MX GPIO init. There was some sort of issue maybe, or maybe I want to look at it in more detail. I'll go step into, and it goes into GPIO init. And then I can go and I can say, hey, step over, step over. So in this case, I'm enabling all those clocks, and then I go a step over, and oh, I want out of here. So here's the step return, which says, okay, finish up the rest of that function and go back to where I was. Now, some of the time, when we get to the point where we're going to be using our TFT, they don't give you the source. They give you the ability to use $10,000 worth of graphical interface code for a TFT, but they just give you a library. So if you pay the money, they'll give you the source code and you can actually go through. So if we tried to step into those functions, or we paused, or to go have a look at things, it might go, I don't know what you're talking about, I can't find stuff, because the source code isn't there. And then you might have to go step return a few times till you get back to your code that called the library, okay? So in this case, I'm just gonna continue on and go there. We can also set breakpoints. So, you know, if I had, for instance, clockwise, I could double click and I have a breakpoint. And then, so if I run this, for instance, I'm running my code and it's doing all that. And then if I push the button, then I've stopped at the breakpoint for clockwise. And then I can step into that function and go through and find out what's going on, or step out of the function, or just continue. And so I can just go and continue. And again, it's running my code all the way till I hit another breakpoint, and then it'll stop at that point. Okay, so, and again, when I'm stopped, then I can go through and say, okay, well, what was count? So I highlight over count, and it says right now count value is 0. Okay, and so you can highlight over some of these and see what's going on. And again, the data trace, which should update. If I have my counts there, it will update and periodically grab data and show me information there. So you should start to see the count happening. But oftentimes there's a history, so what the count was, and then there is also just the individual. You'll see, I've got to even pull it up more, you'll see one value there and then the history here. And then in the console, one of the things I mentioned about that last day was if you redirect printf, hopefully it's all going to work for you. How we did that was to look at the fact that there's a syscalls.c, and syscalls.c has these externals, IO put character and get character, and oftentimes the embedded development environments will give you that kind of thing, and they'll say, for instance, here's write with IO put character. So printf calls underscore write, and that will then call underscore underscore IO put character, which goes and puts out a single character. But they defined it at the top as being external because they don't know what you want to do with it. They don't know what you have attached. They don't know if we have a big debugging environment attached, or maybe a TFT screen, or just a serial port, or what have you. So I can grab the external defined, so it's saying it's in some other location. So I grab that and I put it into the user defined for begin and end between there, so it doesn't wipe it out if I change things. And then I can put what I want for how do you put a character out. And you could redirect it out a serial port. And so I could call a how uart and send it out a serial port. In this case, we have this back channel that is available to us, and it uses send char, ITM send char, to go out that port 0. So we're going to use that. But at times, if you say, okay, I don't have that, or I don't want to put that available, or I want to put it on another console off a serial connection or a USB connection or what have you, it's just redirecting put char. Okay. And so, like I say, a lot of development environments, they just go, I don't know what's attached. We'll leave it up to you. So your printf doesn't work until you go find that low level and do something with it. When we were in 130, it would print with the serial print, but it didn't know how to do floats because, well, they by default didn't set it up to do floats, just like they don't here. It understands floats, but printing them out is quite intensive, and printf is quite intensive. And so on the Arduino Uno, there's about 8K, and if I compile in the ability to print out floats, that takes 1K of it. So here we have a meg. So we've got a lot more. It's not 8K, it's 1 meg. And so it doesn't matter as much, but by default it's not in. But it's just a little checkbox. What you had to do in 130 was you had to change one of the shared libraries that it links in. By default, it didn't have it in it. Okay, so way back at the start, you guys grabbed some stuff and put it in certain directories and things, and that was going to make your programs bigger, but it was so that you could play with printf. Okay, so I just need to copy that over and put it in main and go down to how begin and for and put it in there. Now this makes it, and it's underscore underscore, and again, we talked last day, we have a return 0. The prototype for the function wants to return a value, and return 0 says everything's okay. I could be checking to see that I'm only sending a certain character out, and if it was something else, I could return a negative number to indicate that there was something inappropriate happened, or something like that. Okay, so we put that there. So that means that printf should work. And so if you go to use printf, you might see a little exclamation mark because printf is saying that it doesn't understand what you're talking about. And the error it gives you is implicitly defined. If you see implicitly defined, it means I don't know what you're talking about. I am assuming you're calling some function that returns an int. And maybe that's what you're doing, but it's going to take that guess. Okay, so if you call the function before you defined it with a prototype, it goes implicitly defined. I'm going to call a function, and I'm going to return an int. So if you're returning a float or something else, it's going to garbage it up because it says it's an int. Okay, so that implicitly defined is telling you, I don't know. So you either have to, if I called clockwise, if I don't have the prototype up top in the private function prototypes, it's going to say implicitly defined. It's going to say it'll call clockwise, and it's going to expect you to return an int, which I'm not returning anything. Okay, but it'll say implicitly defined. Oh, go put a prototype up top. When you do printf, it says implicitly defined because it wants your stdio, standard IO library, so include that at the top. This is where I always mess it up, because if I go and I'll go right in there and I'll go include standard IO, right? And so if we do that, include, um, do, do I put quotes or the less than greater than? What's the difference between those two? Anybody? I don't know. They just happened. Okay. Um, this means it's in the development environment. It's part of the C, C++. Go look wherever your compiler is. It's in the header files that are there. This means it's something I did, or in this case, main.h is something my graphical environment did. Look in the directories where that stuff is, not where the compiler is. Okay, that's the difference between those two. But I always screw up and do this. What's wrong with that? Yeah, it's not in user begin, and end. So, and that's awesome. It'll work, it'll compile, and then I go and add a light or an A to D, and all of a sudden it goes, I don't understand printf. It's implicitly defined because it'll wipe it out. Because it doesn't wipe out stuff between the begin and ends that you've done, but it wipes it out everywhere else. And I put all my other code there, and I always put the includes because, oh, there's main. I'll just tuck it underneath it and continue on. And that's what's going on. And it'll work. And it'll work this lab, and then you copy it over to the next lab, and then you have to add something, and then all of a sudden you're getting errors that you didn't have before because it took it out of there. And where I've seen it is main.h. If I've used that in another file because I needed to reference something that I named, like button or something like that, is all of a sudden it doesn't understand anything because it got rid of main.h because I didn't put it there. Okay, so we have stdio. Now the other thing I mentioned was that we need to say that so this will print out and printf as long as your debug has a software viewer running. So let me just go there, and we have in debug, and I go debug configurations. And so this one is the configuration for GPIO. And so it's going to go find a gpio.elf file, that's the compile file, to go run that. But if I go over to the debugger window, it says, okay, auto start, it's running the new debugger backend. And it's got a nice graphical interface on it. We just single step through code and looked at that. The new debugger is quite a powerful debugger, has lots of features. It's typically command line, and you have to give all sorts of command line stuff, and then you see registers and you see all sorts of information, but it's all command line. So they've wrapped it in the IDE and made it so you can nicely single step through code, and in the back end, it's talking to this debugger server to do all of that command line information so that it can do that and show you the variables and all of that kind of thing. So it starts this debug server. One neat thing about it as well is I could have my board attached to another computer somewhere and have it remote, and you can have an IP address. So have all your stuff set up somewhere else, and then just use your machine and go debug to those devices that are hooked up. That has all of those kind of fancy features. It's not it's rare you'll see this, but if you grabbed a package from somewhere else and you were looking at somebody else's project, the debug probe is called ST-Link. There are others, and by default, somebody else's project may have one set up. Sager is a commercial one that you can buy as well. And there's a package called Open OCD, and there are different features. Some of them will give you. We're talking by default on ST-Link, and but you can get some of the other code to be programmed into this chip. You can get the J-Link debugger and that kind of thing. As far as the interface goes, we're using the serial wire debug, which is 2 lines, and if we do serial wire viewer is 3 lines, which just gives us the ability to put a little bit more data in it. So that's what we're using. I can, however, hook up a 10-pin connector and access more lines, and the full ST-Link standalone unit can give you that option. So you can use a full JTAG interface, a full 10-line kind of interface to go over and do that. I don't want to do that. You can specifically, it says, hey, ST-Link serial number, you can go scan, and if you had multiple devices hooked up, you can say, I want to talk to this individual device on there. In this case, we're just letting it do all of that kind of thing by itself. And frequency auto, all of that is all kind of default. But this is what I want to set up, was that serial wire viewer. And so if you don't set this up, when you go to the data trace area, when we had the debug, it just won't click. It won't allow you to do it, okay? Or if you set it up, but this says core clock. So when you go over to clocks, your core clock we've set up for 168 megahertz. Depends whatever your core clock is. If you have a different device, whatever it says your core clock is, has to match there. It doesn't give you an error, just doesn't do anything. Okay. In fact, I think it'll even, as soon as we go serial wire viewer, it goes, yeah, I'm good for that, but it's not matching. So it can't figure out how to put the back end and the data out to you. And so you can ask for all sorts of things and nothing prints out. Okay. So that's just one thing. Make sure that, and by default, I think it comes up to 16 meg or something like that. You do have to change it. Okay. And so as long as I have that, then when I go and debug, it should let me click that and have data come up. The other thing then is we need to make sure that we are going to, so this should all print out and printf should work. One of the things I said about your printf is you need the /n at the end, and it just kind of, this console, what happens is it seems to buffer it until it sees the /n and then it puts it out. So if you just printf hello, you just don't see anything and you go, what's going wrong? And you go look and it's 168 megahertz and you're checking all this. And it's the fact that that is not, you don't have a /n to push it out. So if I go hello /n, you should see a hello printing out if everything worked. What you may not see is the floating point, and that's because we have to initialize it. And so if I go to GPIO or whatever your project happens to be, and I right click and I go down to properties, there's all sorts of things that are available here. And so if I go look at C++, let's builders, C++, we have, oh, this is interesting. It does it nice. You can't really see it here, but build command, what it's actually doing in the background is calling a make. And when we look at Linux, you're going to, on command line, be using the make utility, which looks at a make file and compiles all the things that are necessary. What it's really hard to see on this screen here, but it says make-J8. It sees how many threads are possible in my computer, and it uses all the different cores and the threads available. And so what it's trying to do is, if it has a ton of little files, it'll compile them all separately. And if you used to have to go and do that, otherwise it would just one at a time go and compile everything. So you have a 12-core CPU or whatever, and it's just using one. And so in probably the last year, it's automatically seeing what you have and saying, hey, try to use as much as you can, compile it as fast as you can. So that's kind of nice in what is there. We have something called build variables, environment. It's all kind of set up for you. If I go settings, then there is a whole bunch of stuff here. MCU tool settings. We got MCU settings over here, and there is a checkbox under MCU settings, and it says use float with printf from newlib nano, and it also has a runtime library, says specs nano specs. So by default, that kind of stuff will work. This use float with printf is what you need to use to make you see the floating point when on the the print, so it'll bring in that larger library. If you were trying to read floats with a scanf and bring something in from a serial port or what have you, then you'd need to enable that. But it's just this one. Sometimes you don't. It's using the what's known as the newlib nano library, so it's using a reduced set of the standard C library, and sometimes you might not find what you need, or it's not doing what you expect because something isn't in the smaller library that was in the full C library, and you can use the full library. And so this is kind of reduced, and it's saying, hey, for most times everybody things are good, but you can just use the standard C library if something isn't working for you. I don't know that we'll encounter it, but that's, if you ever see that, it's like something's not available, you're trying to compile it in. You can use the standard C library, just makes your file bigger, okay? But that's where I have to check it off. And it's just check off and then go apply and close. When we're talking about some of this, I also have the C compiler and the C linker here. And so when I go down and look through here, it says this is the C11 ISO C11 plus library in preprocessor. You ever hear of preprocessor directive? Do you know what I'm talking about? Okay. If you have something that you want to tell the compiler before it compiles, you might say, I have an LCD. So you might define LCD, and then you do things with your code. You use pound of, if def, do something, otherwise do something else. You can put a define in here and say LCD. And so if I put it in here, I can in my code go pound if def LCD do something else, do something else. So if I had an LCD, I could redirect printf to go to the LCD, or, and if not, go out to the serial port or something like that. Okay, it's not part of the C code. It's saying, hey, you're setting up stuff and we're going to conditionally compile stuff based on things. And they have some things here. It's just saying it's using the HAL drivers. Okay, so automatically that's the API that you're using. So those kind of things are available in there. Included paths. Included paths saying when you're going to bring everything in, where do you find all the different header files? And so if you bring in some files, you're going to have to add it to it so it knows where it is. Okay, so it has the HAL drivers, all of that kind of thing as well. If I go to libraries, if I bring in different libraries from somewhere, then I will need to tell it where to find them and what the name of the library is. And that's where I find it in here. So there's a whole bunch of setup. And the one that we looked at right now was just to make our floating point work. But there's all sorts of things in here. And I can go apply and close. And it's right click and you go on properties. Sometimes, I haven't seen it in the last little bit, but sometimes people would be working on the code and all of a sudden it wouldn't understand floating point. Your device has hardware floating point. And sometimes people would bring in and try to do things and it goes, well, it tried to, it didn't think you had floating point and was looking for the floating point emulation libraries. So you can have a whole bunch of routines that will do floating point in software routines because you don't have the hardware module to do it. And so that takes up more space, makes it go slower. And sometimes it would forget that you have hardware floating point and you would have to go into the properties and go, no, I have a hardware floating point already built in and I don't need those software routines. Okay. If I forget the error now that it gives you, but it can do that. Everybody good with, we're setting up, first of all, the software, the serial wire viewer for doing our debugging. We're going to, in the debug window, you set up the serial wire viewer trace and the serial wire viewer console. Okay, so we set those up. If I go look at GPIOC, in System Core, you go to Sys, and this is probably got nothing there, but you could set up all sorts of different options, and we just say trace asynchronous software, and what that does is it puts a pin there, and a pin there, and a pin there for our serial wire output. The serial wire trace will work for the 4 variables. If you don't do that, in order to get the printf redirected and have more data going through, you need to have that kind of turned on. Okay, and so it's just a matter of going sys, go trace, and then when I go save, it says, do you want me to generate and update the code? And that should make that whole debug and interface go. Okay. Now, we had the lab where we're saying, okay, we have the thermistor, and we looked a little bit about the thermistor for lab 3. Now, one of the things was I included, this is on our week 3 stuff, I included the MF52D103F3950 thermistor documentation because that's what the Kuman kit CD has on it. But when you go and actually measure the thermistor, it's actually an MF52D104, okay? And the difference is one, by nominal across the thermistor is 10K, and the 104 is 100K. And if you measure across your thermistor, it should say around 100K. And so, and it has all sorts of other information in it, and we looked a little bit about it, MF52D, and that's saying, okay, what type of coding is on it. We have our 100K, the 3950 is something known as beta, whatever that happens to be. And I've included the module from Kuman showing you how to wire it up. We'll just go back into that just for a sec, if I can. I thought it was just going to show, oh, there we go. Wow, that's slow. Huh? Come on. It says waiting for it. Come on. So one of the things you need to make sure is that you're wiring it up right. On the board, you'll see VDD and ground. I asked in the lab for you to wire things up to PC1, and the reason I asked you to wire it up to PC1 is it's right beside a power and a ground, okay? And it's free. It's available for us to use. So that's why I wanted you to use PC1. So there's a ground and a VDD, and if you go look at the schematic, the VDD is essentially your 3.3 volts. And so that's where you want it. And if this, will this actually show it to me? It's still thinking about it. Wow. Okay. So your unit should look hopefully like this. Some I don't think necessarily have the minus on them or that. This is saying minus. That's your ground pin. That's your power pin. And that's your sense pin. So that's going to your PC1. Okay. And so it says sense on this one. So that's where you want that. And so we've got ground, we've got our 3.3 volts or your VDD, and then that's going to your PC1. If you measure across R1, that's a 10K. If you measure across this one, that's about 100K is what you're going to see. That's why I think it's the 104. Okay, so that's where you find that information. And then if I looked at this 104, the M52D, all of that information is saying, okay, what type of coding is on it, all of that information. I guess a lot of people are hitting the internet today. Okay, so M52, a bead temperature thermistor, and we looked at this a little bit the last day, and M52D is this one here, and so it's got a PVC coating on top of it, and then some of the other information is right here. Again, M52D, D is the PVC, and then we have, it says number 3, XXXX is the resistance at 25, and it's a 104, so it's 100K. And then we have our number 4, which says it's an F, so it's plus or minus 1%. And then our beta value is that 3950 here. And so we're going to use that in some of our calculations.
How do you get 100K from 104?
1 0 and
4 more zeros?
4 more 0. Yeah. 1 0 and 4 more zeros, right?
Yeah. Okay.
Okay.
Makes sense.
And like I say, I think there's if you go to the Kuman and you look at the CD, they gave you that one. But if you measure, and I haven't done it to yours, but any of the ones that I've seen so far, when I go across the thermistor, it's 100K, not 10K. So Adafruit has a nice. So one of the things about a thermistor, it's not linear. Okay. And so there's a nice graph that you can see, and you could build a lookup table and say, hey, when I read this, it's going to be this temperature. Typically, they use things like some approximations that are good across the range that you measure it. And Adafruit has a nice little talk about thermistors and how you go through that process. And so if we come up in this, hopefully we'll be able to see it. And so it'll take you through the steps and talk about using a given equation to go and linearize the data. So it says connecting to a thermistor, analog voltage reading, and going through the math to go and figure this out. We read a value in. How many bits is your A to D that we're using? You remember? 10 was the pick. 12? 12? So I go to 0 to what? 10's 1024. 11 is 2048. 12 is 4096. So we go 0 to 4095. Okay? And so in here, it's talking about a 10-bit. So you're going 1023. You have a 12-bit. You could set it for 10, but you have a 12-bit. So bear that in mind whenever you look at things. Your maximum value is going to be 4095. And so it goes through doing the math and seeing that one of the things is that the voltage drops out of it, and it's just a ratio between different ones, and it's showing you how to do some of this kind of math. But it says, hey, to get better readings, then you can do a bunch of things in here to improve kind of the value. And that's just giving you a value, 3,200. Okay, I need to turn that into a temperature. So hopefully a lot of you in the lab last day and today will be able to print out 0 to 4,095. And so what you should see, let's say I see 3,000. When this is a negative temperature coefficient thermistor, so NTC instead of PTC. So an NTC one, when it gets warmer, temperature goes down, or the A to D value goes down. Okay, so as the temperature goes up, your resistance goes down. Okay, so we need to convert that to a temperature. And it says if we have the temperature, not just resistance, you need to do a quick comparison. If I put my finger on it and I see the value going down, hey, I know it's all working, but how do I know what temperature that is? And it says if you want the actual table, there's an equation known as the Steinhardt equation, which lets us do a good approximation, and this is it here. So 1 over temperature A plus our beta with a log, a natural log of R and C and all of this. And you can go and put that in. And it says it's fairly complex and we can simplify it. 1 over T is 1 over T at a known temperature plus 1 over beta, and then the log of the ratio of the two resistors. So that's all awesome. And so you can go and put this in and get your temperature out of it. So, and you can go through and do that and match that all up. But I want to go back here and show you. So you can for sure do that and it'll all match up. There is a NTC thermistors in U. Okay, so if I go to NTC thermistors in U, if it comes up, there is an option to be able to have a spreadsheet. Somebody's gone through and done all of that and made this cool spreadsheet to take your information and generate you a C function that you can copy and paste in your user begin and end for. Okay, and so you just have to call it and pass in your A to D value. But we have to tell it the right stuff if it ever comes through here. Well, let me just see if I can. If it comes up, there is a link to a Reddit page. Don't do that one. There's one that says, here's a Google spreadsheet. Do you want to make a copy for your own use? And you click yes, and then you have to log into your Google account and it'll make a copy of this spreadsheet, which you can then use and adapt. Let me see if I've got one here that I can do that with. Where's my data? Is it there yet? Not there yet. You there yet? Oh, hey, it's almost there. Wow, I can't believe how slow it is today. Wow. I'd love to show you the page because, let me just go in here. Let's go to the drive. Wait, let's see. Yep, still nothing. Wow. There's a few things in this spreadsheet you have to be aware of. If it ever comes up and shows us. It wants the beta. It has a default beta of whatever thermistor they were using. It's different. It wants the other resistor. Your other resistor is 10K. It wants the resistance of the thermistor. I think by default it says 10K and yours is 100K. So you have to put the changes in to all of that. The other thing is, and I almost hate to do this, but let's just see while we're waiting for that to come up. Let me go back to this one. You have to know how your thermistor is hooked up. And your thermistor is hooked up here. Your thermistor can either be hooked up, so we have your VDD, so that's your 3 volts, and we've got a resistor, and then we've got your thermistor, and then you've got ground. So, and we're going off here, what is it, PC1 or whatever, right? And so your resistor is either here or it's here. And so one of the questions on the spreadsheet is is your thermistor tied to ground or is it tied to VCC? So it knows, do you have it like this or do you have that one there and this? Oh, there we go. Okay. And so here we go. And so this is how it's hooked up. So your thermistor is tied to ground. Okay. The spreadsheet will nicely document and give you this function to have that, but we need to know that this is there and not there. It just changes when I go and read. When this goes down, are you reading more or less, depending on whether it's here or here on that voltage divider? Okay. Did that ever come up? That didn't ever come up. Did that? Oh, there's my table. Let's see. I can't believe how slow this is. Come on.
So we need to place that resistor?
It's on your board. When you do ground, your VDD and your PC1, it's there. Okay. I measured the R1 and I measured your actual thermistor for the values to make sure it was right. And the beta is 3950. If you plug it all in, this spreadsheet is going to, down on the lower left, give me the right values and give you a function called convert temperature, which you just pass in your variable into. And then when it returns, you've got a temperature that's afloat that you go and print out. Okay, so that's what you need to do. And you just highlight over the whole block of code, right click, go copy, and you can paste it right into user define 4. Okay, so you can stick it right there. The other one quick thing I'd like to say is, let's say I had temp and equal, I don't know, x divided by 100, or let's say x divided by, I don't know, let's say, I don't know, 150 or something like that. Let's say I have something like that, and this is a float. If this is from your A to D converter and that's an integer, this is an integer. What the C compiler says is, oh, integer, integer. I'll make a temporary space to be able to do that calculation. That's integer. And then I'll throw out the remainder. Okay. And then store it as a float, which gives you not what you're wanting. Okay. So I've had people show up with zeros or whatever. So you can do a couple of things. You can either cast it. So you say, hey, this is a float. So you just put that and it'll go, okay, it's a float. Or you can put a .0 and that tells it's a float, and then you'll get the right answer. Doesn't give you an error, just goes, oh, you know what you're doing. And so it will store it as an integer, throw out all the information you want, because I divided by 150, so I have some sort of decimal value, some below 1 value, and then it stores it as 0 when it gets to there. Okay, so if you get a weird result, put a 0.0 in, or you cast it. It's because this is an int and this is an int, and it says you want a result to be an int, which may be not what you want. Okay, we'll leave it there. Someday this will come up. We'll maybe see it in the lab.